All right, so we're going to wrap up our conversation about transformations today by looking at the last two transformations that we haven't looked at yet. And the first one is rotation, right? So we're to rotate. We've got a couple of things. If this center of rotation, we'll talk about center of rotation in a second, is inside the figure, then the figure will pretty much just turn around, right? Will just sort of turn around itself. If the center of rotation is outside the figure, then what we're talking about is basically attaching an arm to this and having it rotate around a point that way. So it won't necessarily just turn, it'll move and sort of turn, if that makes any sense. And so that's what we're talking about with rotations. So we need to be able to perform a rotation today. Some definitions for you. A rotation is a transformation in which a figure is turned about a fixed point. All we're doing is turning the figure. We're not really changing size or anything, so that means that rotations are going to be an isometry for us. You have to remember what an isometry is, right? It's going to maintain side length and angle measure. A rotation has to have a center. The center of rotation is the fixed point in which a figure is turned about. It can, like I said, it can be inside the figure or it can be outside the figure. And then we have to know what angle, how much to rotate it. And so the angle of rotation will do that for us. The angle of rotation is what is created when you take a ray or two rays and draw it from the center of rotation to the image and the pre-image. So you'll end up having a center of rotation here. The pre-image might be here, and the image might land here, and so that would be your angle of rotation. Okay. Now, in order to perform a rotation, you really need geometry tools. So your protractor, compass, straight edge, that kind of thing. Without those items, then the only other way we can perform a rotation is if we take the figure, put it in the coordinate plane, and then rotate it about some special angle measures. Okay, we'll do the geometry tool rotations in class. We're going to skip that part of the notes. So, in order to make the rotation a bit more predictable and therefore get us into some rules for rotations, like I said, we're going to take the figure and put it into the coordinate plane. And then we're always going to rotate counterclockwise about the origin. So the origin will always be the center of rotation. Remember, the origin is at point 0, 0. And if we do that and rotate in three particular angle measures, if we rotate 90 degrees, 180, or 270, then we have some rules that we can apply to the coordinates that will help us figure out where our shape will land, right? For a 90-degree rotation, you see it here. From our coordinates, all we do is we change the sign on the y-coordinate and then flip-flop them. So change B and then flip-flop these guys. If we're going to rotate 180 degrees, then we just change the sign on our two coordinates. That's what this means, right? And if we rotate 270 degrees, then we change the x-coordinate and flip-flop them, and that's what that means. Okay? So with that, then we can just perform some rotations. So the first one we have is this quadrilateral RSTU with those vertices. And we want to rotate it 270 degrees about the origin. So we plot our image first. So 3, 1 for R, 5, 1 for S, and 5, -3 for T, and 2, -1 for U. And when we draw this in, it looks a little bit like a kite. We won't do any verification of that being a kite, but anyway, if we're going to rotate 270 degrees about the origin, then like I said, we've got some rules that we can put in place to help us figure out where R prime, S prime, T prime, and U prime will land. Right? And that rule is 270 degrees. We change the x-coordinate and then flip-flop them. So change the x-coordinate and then flip-flop them means that R prime is going to be at 1, -3. S prime is going to be at 1, -5. T prime is going to be at negative 3 comma negative 5. And then u prime is going to be at negative 1 comma negative 2. So 1 comma negative 3 is r prime. 1 comma negative 5 is s prime. Negative 3 comma negative 5 is t prime. And negative 1 comma negative 2 is u prime. And so we have translated that kite to here, or what I think is a kite. Now I'm starting to question, right? But anyway, that's it. That's all we do to come up with our new figure. All right? Now you give it a shot. We're going to rotate this triangle 90 degrees about the origin. So stop the video, try it out, and when you start it back up, we'll go through it. So we want to start by plotting J, K, and L. And now rotate it 90 degrees. And if we rotate it 90 degrees, then that means we're going to change the y coordinate and flip-flop them. So change y and flip-flop them. For j prime, it's going to be at 0, 3, negative 3, 4 for k prime, and l prime will land at 0, 6. So j prime, k prime, and l prime. Okay, and so there we go, rotated 90 degrees. All right, any issues with that, make sure you come find me and we'll walk through it, okay? Now, we can also use the idea of a rotation being an isometry to help solve some problems. For example, this standardized testing problem, where they give us this figure, which tells us that this quadrilateral has been rotated about p, 100 degrees, and we want to go find y. Well, here's y. And if we can visualize this a little bit, we will see that 3x plus 1 is the side that maps out to the 5y over here, right? If we rotate that figure over. So we know that 3x plus 1 is going to be equal to 5y since this is an isometry. Now the problem is we can't solve that equation. So we move on. There's a 2x here, and that 2x is is what we're going to get when we rotate this 6, the side that's 6 over here. So we can set 2x equal to 6, solve that for x, and x is going to be 3, which means now we can plug the 3 in for x here and go to work here and find that y is going to be equal to 2. So the answer here is B. Okay? But you have to sort of visualize that a little bit and figure out which side maps to what side. Okay? So that was one for me to do with you now. Here's one for you to try. Go find R, stop the video, and again start it back up and see which of these values, 3, 5, 6, or 15, R is going to end up being. Okay, if we can visualize this a little bit, we find out that, let's see, there's an R here and an R here. This 4r minus 3 side is going to come from this side. So this guy, well, we're rotating the other way, rotates to here. This side backs itself up to here, which means that this side maps to there. So we've got some equations to write. We can go 2s equals 12, and we can go 3r equals 2s plus 3. And so to find r, we've got to find s. We can find s with this equation. S is 6. We can plug in 6 for s. And find out that r is 5. Right? So there you go. And that's about the extent of what we can do with rotations without our geometry tools. So make sure that you have those with you, and we'll try to get to them next time. Okay? The last transformation is a dilation, right? A dilation says that we're going to take something kind of smaller and then blow it up, or take something larger and make it smaller, right? We can enlarge or reduce with the dilation. But since we're changing the size, that means that side lengths cannot be maintained. This is our only transformation that is not an isometry. So we want to be careful not to assume that the side lengths are going to be the same, right? And this is going to be pretty obvious. So we want to be able to perform dilations here. Now, some definitions for you. Dilation is a transformation that stretches or shrinks a figure, and it creates similar figures, right? So they're not going to be equal in size, but they will be similar. The side lengths will be proportional. Now, like rotations, dilations have a center. It's a fixed point that we're going to dilate from. And it's kind of interesting there, too, if the fixed point, if our center of dilation is also the center of our figure, then the shape will just get bigger or smaller. If the center of dilation is off of the center of the figure, say outside, then not only will this thing get bigger or smaller, but it will also shift, either be closer to the point center of dilation or further away, right? So it'll also move it instead of just making it bigger or smaller. And we'll see that in a second. Right? Now, since the dilation creates similar figures, that means that the two figures should have a scale factor. And so we have to know what the scale factor of the dilation is so that we know whether we need to blow it up or make it smaller and by how much. And the scale factor should be consistent whether we're enlarging or reducing. And so the scale factor will always be figured by taking the corresponding sides and comparing the prime to the original, comparing the image lengths to the pre-image, or the after over the before, but it's always going to be the prime or the image over the pre-image, okay? And based on that scale factor, we can figure out if we're enlarging or reducing, okay? And we'll see that in a second. So, for example, here, find the scale factor of the dilation, then tell whether the dilation is reduction or enlargement. Well, we have to see that we're taking the paper clip and we're enlarging it. We're blowing it up. Well, that's what we're seeing now, right? How do I know that? Because the larger paper clip is the one that's labeled as the P prime. So that's the after. That's the image. And so that means P is the pre-image, so the smaller paper clip is the pre-image. So we start with the smaller one and get to a bigger one. So we're definitely enlarging. Now, as far as the scale factor goes, then we want to compare the prime to the original, the after to the before. And we have a distance from the center of dilation for each of these. CP prime is going to be your prime, so that needs to go in the numerator, so 12. And then 8 is CP, that's the distance from the center of dilation to the original figure. And if we reduce that, we get 3 to 2. And so we can obviously tell that we're enlarging. This is enlargement because we're going from a smaller paper clip to a bigger one. But if we didn't have the diagram, we would still know that this is an enlargement because the scale factor is bigger than 1, right? Or the enlargement, or the prime is bigger than the original, so obviously that's an enlargement as well. So just some ways that we can tell even without a figure. Okay? Here's one for you to take a look at. Take a second. Is this an enlargement or a reduction? And then we need the scale factor. So hopefully you're looking and seeing that since this guy is the prime paperclip and this is the original, that we're reducing. And to get the scale factor, we're taking the prime, which is 18, and comparing it to 30. And so we reduce that to 3 to 5. Which makes sense. The scale factor is less than 1, so we are definitely reducing. Okay? And even without a diagram, we can tell. Okay? In this dilation, CP prime is 3, CP is 12. That's the distance from the center of dilation to the figures. Tell whether the dilation is a reduction or an enlargement. Well, to find the scale factor, we always go prime over original, so 3 to 12 reduces to 1 to 4, which means that since the scale factor is less than 1, we are definitely reducing. Okay? Now, how do we perform the dilation? And it's kind of like rotations, where if we have our construction tools, we have a lot more flexibility and we can do a whole lot more with dilations. Without those construction tools, we'd have to place an image in a coordinate plane and set some conditions down and then dilate that way. So in order to see that, there's a file in the module that says Dilations Grid. You need to download that, and you can work through this. Or I'll just show you these two. If you want to just kind of put your pencil down and watch for a second, let me show you what happens when we put this in the coordinate plane. Okay? So, the first one here, I want to dilate, and we'll call it a square because it will be a square, square ABCD with vertices with coordinates for our vertices. Let's go 2, 2 for A, -2, 2 for B, -2, -2 for C, and 2, -2 for D. So we go here at A, B would be here, C here, and D here. And then let's dilate this by a scale factor of, let's say, 3 with a center at the origin. Okay? And if that's the case, if we're going to dilate with a scale factor of 3 with a center at the origin, then all we have to do is take the scale factor and multiply it into the coordinates for our points here. Right? That's how we predictably figure out where our prime points will be. And so if we do that, we get these points here. And then we can go plot those points. So A prime would be at 6, 6. B prime would be at -6, 6. C prime would be at -6, -6. And D prime would be at 6, -6. And then we can draw in our square. And so as you can see, the square has just been blown up, right? It didn't shift at all. It's just blown up because the center of the dilation was also the center of the square. Okay? So cool enough, but let's try another one here. And in the second grid, we'll set up a dilation. Okay, so I'll set it up for you really quick. We're wanting to dilate triangle XYZ with those coordinates and do it by a scale factor of 1/2, and the center of dilation again is going to be the origin, right? And that way we can just take our scale factor and multiply it into all of our coordinates here. And so X prime becomes, since it's 1/2, we're just going to divide everybody by 2. Okay, so our new coordinates are at -1, 2 for X prime, -2, 4 for Y prime, and -4, 3 for Z prime. And what I wanted you to see out of this was when the center of dilation is not also the center of our figure, yes, it will make it smaller, but it also took our image and got it a lot closer. So it shifted it down towards the origin. It pulled it down towards the origin. If we make it bigger, we're going to push it away up from the origin, right? So it can also shift the shape. We're not just making it bigger or smaller. So I thought that would be interesting for you to see. Okay? So there you go with our dilations. Now, to wrap up our conversation here, we want to talk about composites, right? Sometimes we want to perform multiple transformations on the same figure at the same time. And that's what a composite is. It's a composition. It's composed of multiple transformations, right? So there's two or more transformations. Some very common ones are a translation and then a reflection, also known as a glide reflection. Or we can reflect and rotate. Those are some of the common ones. But really and truly, we can put together any two transformations that we want. Okay? And to perform those, it's fairly simple. We just want to do the transformations in the order that we're asked to do them, right? So in a translation reflection, we want to make sure that we translate first and reflect. In a reflection rotation, we want to make sure that we reflect first and then rotate. Okay? So let's just take a look at some. And we already know how to do all the transformations. It's just a matter of applying them. So the first one here, triangle ABC. A is at 3, 2. B is at 6, 3. And C is at 7, 1. Right? And so we're going to make our triangle here. And then the composition, we want to do a glide reflection. So we want to translate, and here's our translation rule. And then we want to reflect over the x-axis. So our translation rule basically just says we're going to slide everything back to the left 12, right? Because it's x minus 12. So when we perform our first transformation, our glide, all of our new points, A prime, B prime, and C prime will land here. But we're not done. We also want to reflect over the x-axis. And we have rules for reflecting over the x-axis. If we wanted to write down the coordinates, then we can just change the sign on the y-coordinates, and that will reflect our points for us, and then go plot the points. But it's also easy enough, since the x-axis is a horizontal line, to just count distances for each of our points and make sure that we go the same distance on the other side. So, for example, A is 2 units away from the x-axis, so just go 2 more units down, and you're going to end up with a double prime. So we need new notation since we're going to have a third figure here. So every time we perform a transformation, we just want to add a prime to it. So now we're going to get some double primes. B prime is 3 units away from the x-axis, so B double prime is going to be down here, and C double prime will end up here. And so now we've performed our glide reflection, and that's where our final shape will end up. Okay? Now, we also want to take a look at, some other glide reflections as well. So your next example wants you to take the same triangle and translate it 4 units down and reflect it in the y-axis. Right, so I'm going to wait a second and let you do that. You've got a grid there in your notes to do that with. Actually, you don't. So just go back up and use the same grid as before, and I'll show you where your final shape should end up. Okay, stop the video, try it out, and then you can start it back up and check yourself. All right, so if you've gotten that done, that's great. Actually, we were just asked for the coordinates of the image. So we could have done this without the grid. So if you haven't, go ahead and write down the coordinates for the pre-image, and then come up with coordinates after your translation, and then coordinates for after your reflection. Then you can start the video back up and check to see if your coordinates are correct. And this is what you should have ended up with, right? When we perform our translation of 4 units down, we just want to subtract 4 units from every y coordinate. And so our after our translation, our a prime, b prime, c prime will be located there. After that, if we're going to reflect in the y-axis, then all we need to do is change the sign on our x-coordinates, and that's how you end up with your a double prime, your b double prime, and c double prime here. Okay? So hopefully that makes enough sense. We don't even need a grid to come up with those coordinates. We can just use our rules. Okay? Now, the next thing in your notes wants you to practice writing your own composition. Okay? So if we come back to our example 1 here, then we want to come up with a composition that will take a double prime, b double prime, c double prime, and get us back to ABC. Okay? There's a lot of different ways you can go about doing this. One thing we could do is just go opposite of our original transformation, right? So to write this glide reflection, it can be a glide reflection if instead of we slide back 12 and reflect over the x-axis, we can do our composition by doing a translation first and go from our points to adding 12 to the x's. That way we can slide it to the right 12 spots and then perform a reflection. But we can still reflect over the x-axis. So if we slide 12 spots back and reflect over the x-axis, we'll end up back to ABC. That's just one way we could do it. You could also talk about doing, well, I was going to say, we can also talk about doing a reflection and then a translation, but that's not going to work. We can't reflect this guy over the y-axis and then translate, right? I guess we could reflect over the x-axis and then translate back. Add 12 to everything, that would be okay. Right? So anyway, just some options for you. Okay? Now, very common question is, do we have to do the transformation, the composition in the order in which we're asked to? That's what the next 2 examples are designed to show you. So let's first do a composition of reflecting in the y-axis and rotating 90 degrees about the origin. We have rules for both of those. So we're going to plot R. R is at 1 comma negative 3. And S is at 2 comma negative 6. So there's our segment. And so we can do this with our coordinates first if we want. So R prime we get, if we reflect in the y-axis, we just change the sign on the x's. So R prime S prime ends up at negative 1 comma negative 3 and negative 2 comma negative 6. And so we can go plot that here and here. And then we want to rotate 90 degrees. So to come up with R double prime, right, we want to change the sign on y and then flip-flop the coordinates. So we get 3 comma negative 1 and 6 comma negative 2. Those rules will be given to you on the quiz. You can find them in your notes. And so R double prime lands here and S double prime lands here, which is a bit unpredictable. It's kind of weird how it ends up back in that quadrant. But if you can imagine rotating it 90 degrees about the origin, that should make some sense. Okay? Now, if we were to perform the rotation first, that's the next example, right? Then do the reflection. How does that change the transformation, or does it, right? So now we're going to go opposite and do the rotation first. And if we do that, then it's the same rule. We change the sign on x and flip-flop the coordinates. So r prime then would be at -3, comma -1. Or hold up, I'm wrong. Sorry. We're reflecting 90 or sorry, we're rotating 90 degrees. So we got to change the y and flip-flop them. So this becomes 3, comma 1, and s prime becomes 6, comma 2. So 3, comma 1 here for r, 6, comma 2 for s prime, r prime and s prime. And so that's what happens when we rotate first. And then if we reflect over the y-axis, we're going to get r double prime, right? If we're reflecting over the y-axis, we change the sign on x. And so r double prime ends up here, s double prime ends up here, and the answer to the question is, does it matter? Yes, it does. R double prime, S double prime in our original composition landed here, and then after we did the changed the order, it ended up over there. So sometimes the order does definitely matter, which is why we want to get in the habit now of performing our compositions in the order in which they're presented to us. Okay? All right, and that is it. Homework is out in Canvas. Make sure you have that done by next class.